Welcome to Brain Vision.
All right, so in this question, we're trying to relate a graph of the concentration rate of the contractile vacuole of a paramecium to the osmolarity of the solution. So let's unpack that a little bit. The paramecium is a single-celled organism that lives in fresh water solution. And I've sort of tried to draw a little critter over here that lives in freshwater solution. Now, because it lives in fresh water, the water outside of the cell, outside of the paramecium, has a lower concentration of solutes than the paramecium. The water outside is hypotonic to the paramecium. And because the solute concentration is higher inside, the water is going to move into the paramecium. Now, if the paramecium doesn't have any compensating mechanisms for this phenomenon, it will swell and burst. But it does. And what I've tried to draw here, sort of like in this little star-shaped thing here, is an organelle that the paramecium has called a contractile vacuole. And the contractile vacuole is like a little vesicle, a little pump that fills up with water and puts water outside of the cell. So water comes in via diffusion and it's actively expelled from the cell via this concentration rate. Okay, now osmolarity is another term for concentration of solutes in water. Okay, so don't let that throw you off. So now the question is asking, what is the relationship between how high the concentration of solutes is outside of the cell versus how fast this contractile vacuole is pumping water out of the cell? So I have one scenario drawn here. Let me draw a different scenario. Okay, so suppose that I have the paramecium again, and this time, let's say I have the same amount of solutes inside, but I have water that is more concentrated. It has a higher osmolarity than the previous case. Well, what would happen in that instance is that you would have less water coming into the cell than in the first case scenario. And the contractile vacuole would have to work less hard because there's less water coming into the cell. So its rate of contraction would slow down. Okay, and that's exactly what this graph is showing here. That's what this graph is showing, right? So at low, so on this side, you have low osmolarity, high rates of contraction. Low osmolarity, so the concentration of solutes on the outside is low. The contractile vacuole needs to work extra hard. It needs to work at a high rate to expel that water. At areas of high osmolarity, the concentration rate is lower because less water is coming into the cell. That's what the graph is telling you. Now let's look at our answer choices. At higher osmolarity, lower rates of contraction are required because more salt diffuses into the paramecium. Salt is not the one that's exchanging place here. It is the water. B, in an isoosmotic salt solution, there is no diffusion of water into or out of the cell, so the contraction rate is 0. That sort of makes you want to say, yeah, that feels right, but answer the question in front of you, not the question that's in your head. The question in front of you is, which of the following is the correct explanation for the data that you're shown, for the data that's in front of you? Look at the data that's in front of you. Does the red line ever reach a point where the concentration rate, or I'm sorry, the contraction rate is 0? In order for that to happen, you would have to extend that line all the way to here. That line doesn't extend to where the concentration, the contraction rate is 0. So choice B is incorrect because we never observe the concentration rate become zero. Choice C is the correct choice. The contraction rate increases as the osmolarity decreases because the amount of water entering by the paramecium by osmosis increases. And choice D is the contractile vacuole is less efficient because of the reduced amount of ATP. There's, first of all, number one, that doesn't make sense. Number two, the data shows us nothing about ATP. There's no conclusions that we can draw regarding ATP from the data that is provided to us. So the correct